Hello, I'm Shawn, a senior space weather forecaster at the Space Weather Prediction Center in Boulder, Colorado. And I'll be talking to you today about space weather, in particular, the effects with regards to technology impacts and the Aurora. So, what exactly is space weather? Well, it's what's taking place on the sun 93 million miles away through the vacuum of space to at and around here, our planet Earth. The impacts to space weather are very wide ranging as listed on this slide. This is just some of the things that can be impacted by space weather. There are many others, but we see things like GPS, in particular accuracy and timing. We see satellite operations. This can be actually problems with the satellite platform, but more likely with communication issues between Earth and the satellite in space. Power grid is very concerned about space weather. We all want our power to come on when we flick the switch. Well, in the worst case circumstances, it is possible there could be a noticeable power grid loss to some of our connection in this country. Aircraft operations, communications, many concerns with regards to space weather, which is why we do what we do here at the Space Weather Prediction Center. Now, space weather storms from the sun that cause these things and these potential impacts to our way of life really is cyclical in nature with regards to the sun. There is an average 11-year cycle with solar maximum occurring about every 11 years as part of that cycle, and in between is lower layers of activity called solar minimum. Right now, in 2023, we are working our way up towards solar maximum, which we expect to be at and around the year 2025, so just 2 years from now. Now, solar activity is always occurring on the sun. Sometimes it's just more pronounced, as you see here on this animation, where we see sunspots. This is about a month's worth of imagery on one of the NASA research satellites, looking at sunspots. We can clearly see the sun rotating, which it does on average every 27 days, and we see these sunspots. The interesting thing about sunspots is they're really a focal point for forecasters such as myself to look at and examine when it comes to space weather storm prediction, because they're generally the most likely sources and locations for a solar storm to occur. We focus on many different things with regards to space weather, but there are three primary areas: solar radio blackouts, radiation storms, and geomagnetic storms. Now, these are impact-based, meaning that when we're forecasting an event, when we articulate that out to the community and our customers, we're really talking about the impact, which is what I just mentioned. The underlying cause of the activity is really what we're predicting, such as you see in italics on this slide: solar flares, solar energetic proton events, and these things called coronal mass ejections and coronal holes. Now, these are all related to our NOAA space weather scale, which you see on the bottom. This 1 through 5 scale of activity for these three same categories. The R equating to radio blackouts, the S for solar radiation storms, and the G for geomagnetic storms. Now, there's levels of activity even below this scale that are important and that we're dealing with and even sending some warnings out for. But it's really when you get to this level that we now become more important and potential impacts as we rise on the scale. Think of windstorms. We have wind levels that the Weather Service is issuing advisories for, all the way up through tropical storm level winds, right? But we don't talk about the hurricane scale until we get to hurricane level winds. Tropical storms can be damaging, right? Same thing here. We get to that level of activity where we start to attribute a space weather scale. HF radio blackouts. That's one of the three main areas of impact. Aviation community, emergency responders, military, all sorts of entities rely on HF radio to this day, bouncing radio signals off our upper atmosphere across lengthy areas of the world to communicate. Air traffic control still does this on transatlantic flights in particular, but oceanic ones in general. And when we have a terrestrial weather event combined with a radio blackout event, this can be very dramatic in the worst case scenario, such as happened in 2017 when hurricanes such as Irma were ravaging the Caribbean Ocean. We had the strongest solar flare that we had of the previous solar cycle during that same time. So people couldn't communicate already because power was out. Telephone lines were shredded. Cell phone towers were pulverized. How did they want to communicate? to help rescue people and do command and control or even communicate with loved ones back in the mainland of the United States, it was with HF radio, and they couldn't even do it under this circumstance. So this is just one of the reasons of many of how HF radio can be impactful when it doesn't operate the way we want to see it operate. The underlying cause for an HF radio blackout is the solar flare, as you see here. This burst of X-ray energy, in particular that we're measuring it by, but across the main electromagnetic spectrum that we look at. We measure these intensities in X-rays, as said, so we use satellites in space to measure their strength. And when we see the event, it's already happening. The daylit side of our atmosphere is already being energized by these events, and therefore we cannot warn on them. We have no way of knowing that they're imminent. Instead, we can predict the probability that they'll happen and even the intensity they may reach over 3 days, but we have no way of knowing it's about to happen, so we cannot do warnings. We do send out alerts when we see them reach the 2 level on our scale. Solar radiation storms, another level of activity, impact-based. These are really driven by solar energetic particles in the forms of protons. Now, solar flares and subsequently radio blackouts are really a result of photons of energy, light, speed of light stuff. Solar radiation storms are not quite that fast, but they are nearly that fast. They can get here in as quickly as 20 minutes, or even in some cases, 24 hours or more. It really depends on where the event source was on the sun and how it can travel here to Earth. But when they do get here at the NOAA scale levels in particular, now we are talking about effects not only to communication efforts with HF radio across the polar regions, it becomes obliterated and impossible for days perhaps, but they also can penetrate into the upper levels of our atmosphere and thus cause physical harm in the form of radiation exposure in the worst case scenarios at the highest altitudes, especially in and around the polar regions. So the aviation industry becomes interested. When we launch rocket platforms into space or astronauts that are already out there in space, they are impacted by these events. Rockets will not launch when we start to get into this scale of activity because of the chance for a catastrophic failure for just one of these energetic particles to penetrate into the electrical components and cause a disruption. That could make it go off course and be cause for a failure of the launch. Satellites in space exposed to these particles can be impacted in the worst case. Still very rare and unlikely, but it has happened in the past, meaning it will continue to be problematic in the future. We measure these by protons, as I talked about, the underlying cause for these events, with one of the platforms in space, our GOES instrument, our geostationary weather satellite, has the observational package on it about 20,000 plus miles from Earth in an orbit that allows it to be there and measure these particles for us, along with X-ray flares for the potential for HF radio blackouts. What you saw here on this animation was the result of one of these energetic particle events hitting a satellite about 1 million miles from Earth that we rely on to look for other solar features. It looked like a blizzard hit the spacecraft. That's what happens when these solar particles hit it. They cause these flashes of light on the instrumentation. So some satellites that maintain their orbital position based off star tracking, this would become impossible. So just yet one of many types of impacts from these events. Geomagnetic storms, the third one on our scale. These really cover the entire gauntlet of concerns for impacts from a space weather storm. So geomagnetic storms are the big one. Not necessarily the most dangerous, but the big one. Many things spelled out on this slide here that are just some of the many items of concern when it comes to impacts from these storms. But in particular, for this talk, it's really about the power grid. That's where most of the money is invested. This is what drives our commerce in our country, is the ability to provide electricity anywhere throughout our country. Well, in the worst case scenarios of these storms, maybe prolonged severe levels, or certainly the 5 on our scale at the extreme levels for longer durations, this has the potential to cause failures or problems with the power grid operations in our entire interconnected country on this grid. In the worst case, it means a failure, perhaps a large-scale blackout, not just over a part of a town or a city or even a county, but statewide, states coverage for a potential blackout. Not that it's going to happen. It's still very unlikely. We have a great power grid control system in our country, but they have to maintain it. And when you introduce extra currents of energy, which happens from these geomagnetic storms, direct current getting introduced onto an alternating current system, that's problematic. That's why we do what we do, and we send out and alert our customers, such as the power grid, about this activity so they can take precautions or stop maintenance or whatever the case may be to keep that grid running. That's why we don't notice an effect. The light doesn't suddenly go off normally because they're taking measures to keep it working. So just because we don't see the effect doesn't mean that they're dealing with the impact. What causes these events? Well, one of them is coronal mass ejection. That is when billions of tons of solar material eject from the sun into space. And by this animation, you can see how that works. This is from a satellite 1,000,000 miles from Earth. It has an instrument called a coronagraph, and that's what you're looking at here. The white circle represents the diameter of the sun. The black circle is simply a disk blocking the brightness of the corona and sun itself from being seen, so we can focus on that lower corona. And we saw this burst of plasma eject from the sun in the top left part of this image, and that happened in just 4 hours of time. And these expand, as you saw, as they move into space. So we as forecasters, when we see these events, we have to forecast the chances that that expansion, 93 million miles is a lot of expansion time, could actually reach Earth. Sometimes it's a bit more obvious, and we see something called a full halo coronal mass ejection. So in this case, it's clear that that ejection is either coming directly towards Earth or directly away from Earth. We don't actually have the ability on that spacecraft to tell by looking at it alone which way it's going. During solar maximum, as you can imagine, if we have a whole bunch of sunspots littering the face of the sun facing Earth, there's likely something similar on the other side of the sun facing away from Earth. So just because we see this, we don't automatically assume it's directed towards Earth. It could be going totally away in the opposite direction. But we have other resources we can call upon and look at, including other imagery, other measurements of data and observation signals that the U.S. Air Force helps provide us and their radio observation and optical networks. And we can use this to help determine where it's going. Is it coming towards Earth? And then if we decide that, now we go through processes to help figure out, okay, when might it get hit here? And if so, how intense might it still be when it does arrive? And therefore, we can put watches out for this activity. Remember, for solar flares and radio blackouts, we can only alert on them. For solar radiation storms, we can actually alert on them and even put out a little bit of a warning. Very little lead time in some cases, but we can warn on them. For geomagnetic storms, we can do the whole gauntlet from watches 1 to 3 days out to warnings and ultimately to alerts as we reach each level of the scale. This is an example of some of the things that we go through with just geomagnetic storms alone, not even talking about the other categories. Now, when we measure geomagnetic activity, it's really about the deviations in our magnetic field from instruments on our planet. That's how we measure Earth's magnetic field. That's how we can tell that a magnetic storm is going on. So as a CME arrives, for instance, to Earth, it hits our magnetic barrier, our magnetosphere. And if it's strong enough, it's going to start to generate or cause increases in the natural currents that result from our magnetic field and solar wind interactions already. But when we increase that energy output from these storms, that can cause increases in the current, and thus the deviations in the magnetometers and so on and so forth. Lots of detail here, but bottom line is we measure this on a scale. That scale is called the K scale. It's an estimated planetary-wide scale that we use here that we base our forecasts off. We have a 1 through 4 on that scale. When we get to 5 on that scale, now we're at G1 on our NOAA Space Weather Geomagnetic Storm Scale. So here you can see at K of 4, we're already putting out a warning, even though that's not at the NOAA scale of G1. We get to K of 5, now we're at G1. So we're issuing some additional warnings, and we're also making a few phone calls to a couple of power entities in the northeast part of our country. When we get to G2 on our scale, a K of 6, now we're talking to NASA for the safety of the astronauts on the space station and for comms issues, and air traffic control out on the West Coast. When we get to a K of 7 or a G3, now we're on a conference call with the entire power grid of our country Not that something's going to happen or even close to likely to happen, but they all want to know now. They're going to see things on some of their equipment, and they want to know what's causing it. When we get to a G4 or a K of 8, now we're talking to the Emergency Response Bureau of our government, FEMA, the Federal Emergency Management Agency, as well as everything below still going on for each of these levels. And even more when we reach a G, a rare, very rare G5 level. So this gives you an idea of the types of things that we're doing. We can warn on these. We send watches out through G3 for these events. We just encapsulate as G3 or higher. Beyond that, for warnings, we go out through, we go through G4 for our watches. For warnings, we only go out to G3 or a K of 7, and alerts we do for every single level as we reach them. And these are measured over 3-hour periods. So here's that gauntlet I was just talking about, watches, warnings, and alerts, as related here and just shown on the G scale alone, from minor through extreme levels of activity. Where are we at in the solar cycle right now? Well, as I mentioned, we're in solar cycle 25. That red line represents the forecast done by an international panel of scientific experts on this. That's their prediction. Roughly in about 2025, that would reach a solar maximum similar intensity to last cycle, which was nothing extraordinary. However, the blue line plot shows where we're currently at compared to that forecast. We're above and on the top fringes of the margin of error, and even sometimes above the margin of error, outside of that. What does that mean for the solar cycle? Well, we don't know. Does it mean it's going to happen earlier, a solar max? Maybe. Because remember, it's just 11 years on average. Does it mean that we're going to have a stronger one than anticipated? Possibly. We don't have no way of knowing that. It may just stabilize and even out or decrease again, fall in line or go lower. The sun is a mystery. It's still very difficult to tell what ultimately is going to happen over the course of a solar cycle, even as we see its progression unfold. Anybody can find information about space weather activity and what our forecasts are, current watches, warnings, and alerts, all on our webpage at swpc.noaa.gov. It's free. The taxpayers are paying for this. So everything we can possibly put on there is out there. And what and who in the community really wants to know, as far as average people goes or hobbyists, they really want to know about the aurora. Will they see the northern lights, for instance, in their part of the country? That's what we're talking about next here in this talk. That effect alone is probably the most extraordinary thing that we see with regards to space weather, storms, and activity. And it's a result of geomagnetic storms. So it really equates to our G scale of activity. Where can you find out about what we're doing? We do not do aurora forecasting from SWPC. That is usually done by private companies and enterprises. So if you want to get more detailed information about aurora, you can look for those things and subscribe to them. What we do is put out forecasts for the activities I talked about. However, we do have some information out there about the aurora. And one of the things we have is the ovation model, or the kind of a 30-minute forecast of the aurora. And some of these things can be found right there on our webpage. And we have an experimental aurora dashboard out there, which is hoping to be operational soon. And you can go there even right now and take a look for yourself and find out what the forecast is and a lot more information about the aurora itself. What causes it? Really, electrons. Electrons driven in the solar wind, in particular by these coronal mass ejections or other features that I haven't talked about, that drive electrons. And when things connect, they can get into our magnetic field lines that come down into our polar regions, especially from behind Earth and what we call our magnetotail. And they can rush in by changes, drive their way down into the outer layers of our atmosphere, and they react with other molecules and atoms out there. And that's eventually what really causes the aurora, is this injection of precipitation, if you will, of electrons going deeper into our atmosphere through our magnetic barrier, that magnetosphere, and in particular, as I said, from behind Earth in the magnetotail. What makes it appear? It's that interaction between these driven-in electrons and the atoms and molecules which already exist in the outer layers of our atmosphere, mainly the ionosphere. What happens is these come into our outer layers through those field lines I talked about. This transfers energy and kind of excites the particles that already exist here in the outer layers of our atmosphere in the forms of molecules and atoms, makes them go into higher energy states. And when that energy begins to relaxes, light is emitted in photons. That's what really causes the aurora. And it looks like shimmering curtains often because it's in these magnetic field lines. So it kind of sets that an idea that these actually exist out there, even though we don't normally see them. So that's really what drives and makes the aurora appear. There are different colors in the aurora. Red is less common. Green is certainly the most common in how people usually see it. What makes these colors? Well, it's really about the elements that are out there and the heights in the atmosphere that they are. Now, I am not an aurora expert. I'm really conveying some information to you. If you want to get more information about the aurora, like I said, go to our dashboard. There's all sorts of great information there that really details more scientific basics about what causes the aurora. We see green most frequently. That's because oxygen is a very common element in our atmosphere, and this is what usually is being interacted with at the right layers up there. Red is less common, and it's a state of oxygen that exists a little lower than the 250 miles area, 100 miles or so, 80 miles up to 250 miles, where we see the green. So at the outer layers of that, around 180, we see this interaction that causes red. And sometimes there may even be a purple seen, and that's really a result of nitrogen in its different states of energy. So as I said, I'm no expert, but I'm giving you this information so that you can go more if it interests you or you want to know what causes this. You got a basic idea, and you can really find it on our webpage. What does it normally look like to people when visible? Well, it can be quite a range. Usually, if you're going to see it and you're on the fringes of possibility, it's going to be like you see in this picture on the left, just this green light off in the horizon. That's the aurora, way out there, probably maybe even outside the realm that could be seen based off the 30-minute forecast, for instance, of where the aurora could possibly be seen. If you're lucky enough to have it occurring higher overhead or further up the celestial dome, well, then you may see these shimmering green curtains of light. If you're really lucky, you might see these reds or even these purple fringes of color like they get to see out there in Iceland or Alaska or these far northern areas that really get to see these light shows in the sky much more frequently than we do here in Colorado, where it would normally take a G3 storm or higher to be able to see it. And it really depends on where you're at in the country. And that Aurora dashboard does highlight a lot of that information about when and where you might be able to see it and what intensity level it would take to do that. How far will it go? That's what I was just talking about. And here we can see an example of that related to the K scale or the G scale on that image on the right. The aurora is occurring even on the daylit side of our planet, just not as far southward. You just don't see it because of the light from the sun, but it's more intense on the dark side, not just because that's where it's night and dark, but that's where the magnetotail injection is coming in, where these particles really speed up and come in and can go deeper and further equatorward on that side facing away from the sun. That is pretty much the essence of what I wanted to talk to you about today and was glad to share with you. These are some names and contacts that you can reach out for if you have customer concern needs or if you want to find out more information and can't find it on our webpage. Perhaps they could point you in the right direction, and we're happy to do what we can to give you answers for what you're looking for. And with that, it's been my pleasure to talk to you today, and enjoy any future lookings at this presentation.